Why exactly does the bounce of a spring speed up at the middle and slow down around the edges as it bounces back and forth? The total energy in a spring and mass system stays constant, but the energy form shifts from potential energy to kinetic energy as it oscillates in real time. And when you can solve energy problems relating to simple harmonic motion, you're able to track how bouncy a system is. You can predict speed and compression at any point, and you can solve for things like velocity, amplitude, and turning points without knowing acceleration or force. First of all, where does that energy come from? Because the spring isn't going to move on its own if you leave it alone. When you pull a spring or you push a spring, the initial compression or stretch gives it energy. So you're adding energy into the system. And until you let go, it's stored as potential energy, which is given with this formula when it comes to springs. This may remind you of Hooke's law, which was the formula from the last video. So that's where the energy comes from in the first place. What about the total mechanical energy in simple harmonic motion, assuming no friction? The total mechanical energy is the combination of all of the kinetic energy in the system, so how much it's moving up and down, and all of the potential energy in the system, so the stored energy that eventually makes it move up and down. The total amount stays constant. It's completely conserved. All it does is it switches form in real time. Sometimes there's going to be more potential energy, but to compensate and to keep the total energy the same, kinetic energy will decrease. Sometimes along the bounce path, you're flying faster, so potential energy decreases to compensate because it's turned into kinetic energy. For example, if you have your spring and you're pulling it as hard as you can upwards and you're holding it there, it's not moving, so there's no kinetic energy, but potential energy is at its maximum. When you release it, some of your potential energy gets shared into kinetic energy as it starts moving. I've drawn the motion of the spring at different points in time, and this red dotted line is going to be the equilibrium point, so its natural resting length. Going to analyze what's happening at each point. So at the bottom, you're pulling it down as hard as you can, and you're ready to release it. At the instant you release it, what happens? There's maximum stretch, first of all. And because there's maximum stretch and your spring is at the very bottom, it's as far away from equilibrium as possible. Your displacement from the center, x, is equal to the amplitude, which is the maximum length. Velocity at this point is equal to 0, because you just let go. And all of the energy, the total energy in the system, potential energy, 0 kinetic energy. The total energy is equal to 1 over 2 Ka. Why Ka squared, not Kx squared, like the formula we discussed? A is the amplitude. And when your distance is the amplitude, that's the maximum potential energy. So that's the total energy in the system. How about in the middle, when it's moved into equilibrium? There's no stretch because it's at the center. The velocity is at its maximum. And all of the energy in the system is kinetic energy, no potential energy here. This is similar to what was going on in the last video where we were looking at the velocity, force, and direction at different points on a spring's path. But this time we're analyzing energy. And since all of the energy is kinetic equal to 1 over 2 mass velocity squared, the kinetic energy formula. And there's a lot of formulas, so if I was you, I would go get the cheat sheet in the description for free. How about point 3? What's going on here? What's this weird drawing? This means that anywhere between these 2 points, so either at max stretch or at the center, anywhere between these 2 points, energy is split. So some of it is kinetic energy, some of it is potential energy. Nothing's at its maximum, so it's a ratio. So total energy would be equal to whatever the kinetic energy is at the point, plus whatever the potential energy is at that point. And that's equal to total energy, 1 over 2 Ka squared. This equation is very important, and it's what we're going to use to solve our problems. Of course, it's also on the cheat sheet. So before we solve the problem, let me recap. The big picture is, as your spring moves up and down, or left and right, whatever, as anything oscillates in simple harmonic motion, it's an energy exchange system. And specifically for our spring mass systems, at the maximums, potential energy is maximum. It takes up all the total energy in the system. At the center at equilibrium, at its fastest point, the total energy is all put into kinetic energy. Anywhere in between, it's a split between the two. Problem time. And I recommend you get the cheat sheet in the description so that you don't have to pull these new formulas out of your brain. A child has a bungee cord and he's tied it to a playground and he's got an action figure of, let's say, Batman. He ties Batman to his bungee cord. So his bungee cord, it's 0.15 meters. And Batman, here, we're just going to draw his head. Batman weighs 0.35 kilos. The kid grabs Batman and stretches him down by another 0.1 meters. And then, when he's at this point, he is released back up. We're going to solve 5 different things. I want to prepare you for these kind of problems. The first thing we're going to solve, how stiff is the cord? So how hard is it to stretch Batman up and down? 2, what's the total mechanical energy in the system? 3, the speed at the equilibrium, so right at the center. 4, the speed when he lowers it 0.05 meters below equilibrium. 5, the acceleration at that point. Let's do this step by step, starting with the stiffness constant. If you remember from last video, what happens when you have a spring mass system like this that's being affected by gravity? So it's vertical. We know that the restoring force is equal to gravity's weight. That's how it stays at its natural length. With this formula, we can rearrange for the stiffness constant, which is K equals weight over stretch displacement. And this is at rest, by the way. The weight of the action figure is 0.35 kilos multiplied by 9.8 divided by 0.15. This gives you 22.9 Newton meters. That's our first answer. That's how stiff the cord is. And we're going to write all our answers right here because we're going to need them later on. Next, total mechanical energy in the system. This is going to help us find speeds later. An easy way to find the total mechanical energy in the system is to find the energy when it's at one of the ends. Because one of the two, potential or kinetic energies, is at its maximum. Then we only have to find one. So at its maximum, the equation is this. This being amplitude, this being the stiffness constant we just found. This being the total energy. Plug in our values. So 1 over 2 times our constant multiplied by the amplitude, which is 0.10 meters. You can't forget the exponent. This is equal to 0.1145 joules of energy. This is the total amount of energy. So potential energy and kinetic energy at any point added up will equal this value. Let's set this value aside as well. So this was question B. Now we're looking for speed at the center. At the center, or x equals 0, all of the energy has shifted to kinetic energy. It's the equilibrium, so maximum velocity. The equation that gives us velocity will be this, because we know everything else. We just need this. Our super rearranging skills isolate velocity, or this equation, and just plug in our values. So, total energy times 2 divided by the mass under the square root. The answer is roughly 0.809 meters per second. So, as it's flying through the center, Batman is moving this fast. For the fourth problem, we're looking at his speed when he's 0.05 meters from the center. That's actually halfway up. Let's set x to 0.05. That's the displacement from the center. We can use our energy equation, which is kinetic energy plus potential energy. And we need to consider both because it's not at the center, it's also not at one of the ends. So both potential energy and kinetic energy is present. Let's find both of these values one by one. The potential energy at this point is given 1 over 2 kx squared. We know k is 22.9 from our first question. And the displacement is 0.05 squared. Don't forget that squared. Gives us 0.0286 joules. How about the kinetic energy? We can't just plug and chug with this formula because we don't know the velocity. That's what we're looking for. Here's a fun strategy. Let's look at the maximum kinetic energy possible, which was 0.1145. This was when it was flying through the center. Now, the total mechanical energy is a combination of kinetic and potential energy. It's the sum of the two, which means that the total energy at this point would be this potential energy value we found, plus whatever value of kinetic energy that makes it equal to this value, which was the total mechanical energy in the system, which is always constant. So we can subtract 0.028 from this value. This is the total energy minus the potential energy, because all that's left over would be kinetic energy. This is 0.0859 joules. That's the kinetic energy in the system. That's potential energy at this point. Now we're ready to solve for Batman's speed. At this point, we can find speed with the kinetic energy formula. And we're going to do the same thing. We're going to use the rearrange formula that solves for velocity, which is V equals 2 times energy over mass. This is 2 times our kinetic energy, 0.0859, divided by its mass, giving us roughly 0.701 meters per second. That was satisfying to solve. Now for the final question. What is his acceleration at that point? So at the point that we were solving for, acceleration would tell us how strong the restoring force is at that moment. That's why you would solve for acceleration. It's good to know because it tells you how fast the motion is curving back. There's a lot of formulas. This is why the cheat sheet helps. The acceleration for systems like this is this formula, which we got in the last video by combining Newton's second law with Hooke's law and then rearranging for acceleration. We know every value here. The stiffness constant is 22.9. Mass is 0.35. And the displacement we're solving for is at 0.05 meters. This gives us negative 3.27 meters per second squared of acceleration at that point. That's every problem solved. And we know all this awesome information about Batman's speed and how he's bouncing up and down. So the key takeaway from solving this problem is that energy gives us the velocity at any position. Acceleration comes from force analysis, and together you can track stuff without knowing time. Notice how we didn't have a time interval. We don't know how long it takes at all. We don't know the period, but we were still tracking speed at every position. This makes studying 10 times easier. Go download the free cheat sheet in the description, and I'll include a free surprise worksheet from my premium study kit to help you understand this topic.